Sorry about that. Okay, well, we'll run it again. It's a good thing about GIFs, so they start again. So yeah, so in the 90s, we had the kind of exoplanet revolution, these radial velocities found for giant planets, and then the first transiting planets were these hot Jupiters in the top left. First small transiting planets found by Kepler here in the kind of bottom left. And then we have also, I need to click the screen. We have also this smattering of other colors out here. These are microlensing and directly imaged planets. And the solar system planets have kind of been untouched by this detection bonanza that we've had in the last 20 years. Earth is still relatively not explored in terms of parameter space, but interestingly, Jupiter is hidden behind exoplanets. So that's, at least for the giant planets, we're able to start really finding solar system analogs, but we're still missing kind of Earth-sized planets. But one thing, of course, these are all colored for their detection technique. And I think it's key to say is that not every detection technique is made equally. Some are better than others, and the best is the transiting ones. So at least at the moment. So transiting planets, at least with the observatories we currently have, they are key. So let me click OK first. Right. So, of course, when we see a transit, a planet passing in front of its star, if we know the stellar radius, then we know the radius of the planet to a good precision. So we get at least one first order of the size of the planet. If we also independently observe the star with radial velocities, we can derive the mass of the planet. So mass and radius gives you some first order information on the composition. You can derive the density. You know whether it's pure rock or whether there's gas or volatiles there. But also very key at the moment is that we can do transmission spectroscopy. So these are the planets for which we are able to probe the atmospheres, because during a transit, light filters through the atmospheres. And if we have a precise enough spectrograph, which we now do in the form of James Webb, then we can work out what's in the atmospheres of these planets. So only transiting planets can be deeply characterized in this way. Another important factor is bright planet host stars. So this is also important. One reason is the brighter the star, the more photons we can get from these stars. So the more precisely we can characterize them. So we can go get better radial velocities because we have more signal from our telescopes. We can get better stellar characterization, stellar parameters, which of course there are groups here working on that sort of thing. And we can do more precise planetary radius from the photometry because we get more signal once again. And the brighter the host star, we also get better transmission spectroscopy signals as well. So, so we need really in order to find and understand planet formation, planet composition, what we need is a large sample of planets orbiting bright stars that we can then characterize and discover properties of these planets that we currently do not know. And if you look at all of these 4,300 transiting planets, it looks like we have a lot of planets to work with. But actually, if you start looking at the ones we can characterize in detail, so if you look at the bright stars, and this is V at 11.5, which isn't even that bright, but we remove 80% of them. So we're now only down to 700 planets orbiting bright stars. And if you look at before TESS, which I'll speak about in a second, we only had about 100 planets where we would be able to get a good JWST spectrum. So TSM of greater than 4, that's the kind of signal to noise we expect with JWST. And then when TESS came along, that boosted by a factor of 3 and also filled in a lot of these so-called sub-Neptunes. So planets between 2 and 4 times the radius of Earth. We have a large population of these we can now work with. It's also worth mentioning that actually this corner up here, these are the hot Jupiters. These are the easiest planets to find because they create the largest transit signals. And we effectively know all of them now. All of the stars out to about a V magnitude of 13, so that's within a few hundred parsec. We know all of the transiting hot Jupiters. So there's none left to find up here. But there's a lot of planets here which we're missing, which we haven't found yet, which are orbiting bright stars, which could be the target to observe with JWST and get the best transmission spectroscopy and help us fill in some of the gaps that we have in understanding of planetary atmospheres and formation. But we don't have those planets yet because we haven't found them. So that's a little bit why I'm working with CHEOPS. But let's talk a little bit about TESS first. I showed you how it tripled the number of characterizable planets that we found. So TESS is a survey satellite, the Transiting Exoplanet Survey Satellite to be precise, scanning the whole sky, looking for transiting planets around bright stars. And it does so in this interesting kind of pattern where it scans each hemisphere once per year. But the majority of the sky only gets 1 month observation at a given time. And so if you look again, this in terms of magnitude versus radius this time, TESS has been able to find much brighter planets orbiting much brighter stars than this kind of cloud, which was the Kepler clouds, which tended to orbit much, much fainter stars. And so this is really useful because this is where we can characterize planets. And it's easier to characterize, especially for these smaller planets as well. And so if you look now in terms of orbital periods, again, so this is Earth and Neptune. So these are the kind of sub-Neptune super-Earth regime here. This 27-day line, this is the typical sector duration. So how long TESS typically stares at a star in the sky. And in this case, we see that the TESS dots kind of follow the Kepler dots, so that the planet population is roughly the same. But about here, they diverge. So there's very few TESS planets filling in this kind of longer period regime where we would expect to find planets. And the reason is because TESS is missing. TESS doesn't observe stars for long enough to find planets on 50, 100, 200-day orbits. So this is a real issue. So that's where kind of CHEOPS comes in. So if you haven't seen it before, this is what it looks like. It's about the size of like an American fridge. So it's a 30-centimeter telescope on a low Earth orbit dedicated to transiting exoplanets. It's very precise, so much more precise than TESS. So roughly a 20 ppm precision for a transit around a star, like the magnitude of 9. So that means roughly Earth-sized planets can be detectable in transit for those stars and brighter. It's an ESA S-class mission. I think the only one. For some reason, they stopped doing it after CHEOPS. I don't think that's any indication of CHEOPS itself. And ESA and Switzerland both contribute, as well as some minor contributions from other countries like France and Spain. Its primary mission was for 4 years, ending in mid-July, but we're in the first extended mission, and there's likely another extended mission taking us to 2029. And it's roughly split between the GTO, which I'm a part of, and this open geo call that ESA runs. So anyone can apply for CHEOPS time. And actually, there's only a factor of like 1.5 to 2 in terms of competition. So it's quite easy to get time on CHEOPS. There are a bunch of Spanish members on the GTO, on the science team. So some of these names you'll recognize. Annoyingly, probably for you guys, it's dominated by the IAC, so Enrique Pae and Roy Alonso and Eva Villaver. They're all in the IAC. And I would say that actually CHEOPS has been underutilized by the Spanish exoplanet community. And I think there's it's very easy to get onto the GTO to get your targets observed. And so there's a lot of and it's very easy to contact some of these people and to become part of the GTO. I know some people here in the Institute go through the GEO call, but I think, there's definitely scope for Spain to improve the amount of effort that's put into CHEOPS, I would think. Okay, so a good comparison for the precision of CHEOPS is looking at the Kelt 11b light curve. So this is a hot Jupiter, which was initially discovered from the ground. This is the ground-based light curve where they first detected it. It's actually a combined transit, so 9 different telescopes data combined, and then you see the dip from the planet here. And the signal to noise is only about 20, so it's very large scatter. This is what, even despite a large effective aperture, we know that telescopes on the ground struggle with the atmosphere. When you look at TESS, which is only a 10-centimeter aperture, it looks a lot better. We boost the signal to noise to about 100. But if you look at CHEOPS, we go even better again, a factor of 3.5 in the signal to noise. So we can go to a much nicer looking transit. And we start seeing features that are due to actually the stellar activity that we couldn't see from the other telescopes. So this is a good kind of demonstration of how much better CHEOPS can be than our other facilities. Of course, if you go to Hubble or JWST, you get much better, but good luck just trying to observe for as long a time and the targets you can do with CHEOPS. So it's the primary goal of CHEOPS is characterization. So it stands for the characterizing exoplanet satellites, and one of the major ways that it's been doing that is by atmospheric measurements. So effectively by looking at the phase curve and the eclipse of hot Jupiters, you can measure something about the planetary atmosphere. So the reflection of the planet as it passes behind. So here is the eclipse this is a visible wavelength. So this tells us something about the albedo of the planet, which in some cases can be due to clouds. And in this case, the phase curve and the transit measurement actually told us something about the shape of the planet itself. This is WASP 103, where CHEOPS data helped show that it's actually a oblate spheroid rather than a sphere. And then, but there's been lots of measurements with CHEOPS of characterizing planets this way, observing secondary eclipses and looking at the atmospheres. But that's not what I'm going to tell you about. I don't work with atmospheric data, so I'm going to tell you a little bit about how CHEOPS can actually detect planets, or at least contribute to detecting exoplanets. So there's two things we can do that we can use to kind of try and do this. So we can use the fact that we have better precision than TESS, and we can also use the fact that we can target the times of observation, whereas TESS just looks at the sky this time. That's all the data you're going to get, and then it goes to look somewhere else. One way that we've been able to do this is just being lucky, which is, sometimes you get lucky, sometimes that works. So Nu-2 Lupi was this bright naked eye star, which TESS actually found had, there were 3 radial velocity planets, so planets found by the RVE technique. TESS found that 2 of them transited, and CHEOPS wanted to just look at the transits to improve the radius and look at those planets. And it happened to also catch the 3rd planet in the system, which was 110 days, completely luckily. I mean, we got seriously lucky because we observed for 1 day, and we happened to get something at 100 days. So it's about a 1% chance of that happening, but we caught it. So that was a really interesting first this was within the early science program of CHEOPS. First clear sign that we might be able to use CHEOPS to help confirm small planets. So these are both only about 2 Earth radii, so they're relatively small compared to most of the planets found. And then another case where we did this was we were observing a multi-planet system, TOI 1233, which had 4 known planets, and we found an extra bump in the CHEOPS light curve, which turned out to be from planet F, and we were able to confirm a 30-day orbit for that planet. We can also use radial velocities to tell us information about when the planets might transit, so we can target those stars with CHEOPS. So maybe in a multi-system where one planet is transiting, we can identify outer planets that we can find with CHEOPS. And so we've done this a few times. So TOI 561 D and E was one case where we managed to confirm 2 longer period transiting planets. So this region here is the radial velocity expected time of transit from the orbit that we were able to get from the RVs up here. And so you can see that we found a transit right at the expected, or just after the expected time. So this is all those planets that we've been able to kind of detect this way. So there's another one here, which I can't talk about. It's submitted to us, and we're waiting for a 2nd or 3rd referee report at this point. But the reason it's interesting, it's quite faint, but it's an N-dwarf. And actually this planet out here has an equilibrium temperature of only 300 Kelvin, so it's relatively cool. But yeah, you'll see that one in a few weeks, months. We'll see how long the referee process takes. And then, so these green points are the other planets that we've confirmed this way. And the blue points are the planets that were known already from TESS observations. And so here's another list of planets that we found. In the case of HD 93963, we've spotted in TESS a low signal to noise candidate that was actually very close to the star on like a 2-day orbit, and we used CHEOPS to confirm that it was true. It was indeed there. Similar story for HIP 29442. 2 planets this time, super Earths, so about 1.4, 1.5 times the radius of Earth. There was a hint in TESS of these planets being there, and then there was a radial velocity campaign which also identified them. and CHEOPS was able to come in and confirm that the planets exist and their radii as well. TY1260, there was an outer planet which hadn't been found with TESS, which we were able to confirm. A really interesting case was TY178. So this was 3 years ago now. This is a 6-planet resonance chain. TESS only found 2 planets and actually misidentified some of the other planets in the system by putting the transits together in the wrong way. So CHEOPS was able to come in and solve the system, found that there were actually 6 planets there, found the signals of 2 interior planets that hadn't been spotted because the signals noise was so much better. Yeah, so this is a really interesting example of a Laplace resonance chain, which we don't see many examples of. TRAPPIST-1 is another good example, or the Galilean moons. And actually, there's now, because this is quite a bright star, and it's Endorf, there's JWST observations last year as well. So we now have some information on the atmospheres of these planets, which is really interesting. Okay. Another planet I can't yet talk about. This is a warm giant planet, so a Jupiter-sized planet, but actually it's relatively low mass, only 100 Earth masses, with an outer companion that we were able to identify in TESS that hadn't been picked up, and we confirmed with CHEOPS. And then another system where I identified 4 additional companions to the TESS planet, and we confirmed these with CHEOPS. But yeah, I say in prep, but we don't even know what paper that's going to go in yet. So this is what they look like in terms of magnitude and radius. So you can see that they're, again, following the kind of TESS pattern of finding these smaller planets around bright stars. But the thing that I'm mostly working on is looking for targeting planets with longer periods which have been found in TESS, specifically geotransit programs. So I'll tell you a little bit about that. First, why might we be interested in these longer period planets? So these are the planets where the atmospheres and the orbits aren't dominated by the host stars. So there hasn't been tidal effects on the planetary orbits, like circularization. There probably hasn't been as much flux loss, so atmospheric inflation or atmospheric photoevaporation, which would change the atmosphere of the planet from the primordial state. So by going for longer period planets, we can actually more probe primordial atmospheres. And these are also cooler atmospheres where we can we're able to probe different molecules that are found for close-in planets. And also there's a potential trend in JWST where it finds clearer atmospheres at cooler temperatures for these sub-Neptunes at least. Possibly because at some point water condenses out of the atmosphere and leaves the atmosphere more clear. So that's another reason why longer period planets are interesting. And this is also where you have stable features, so stable exomeans, stable rings, close-in planets. Typically, any of these features would just be removed from the planet by the effect of the star. So how do we find some of these longer period planets where TESS isn't able to? So if you look at a TESS light curve here, so this is the 25 days that TESS observed in sector 12 in this case. I mean, you can see quite obviously this is a transit feature. This is the sign of a planet blocking its star. It's also extremely small, so only about 500 parts per million. So we know that this is a small planet. And then when TESS re-observed, in this case, if you look at the time axis, it's about 700 days later. We see the same signal again. These cases aren't picked up by the TESS algorithms that they use to find planets. We were lucky enough to have an amateur who just looks at all of the light curves. And he sends me a list of good candidates, and he sent me this one. And then I looked in the second new data came out and saw that there was a second transit. So the human eye is still useful for some of these observations, but this is such a clear signal that any simple technique would also be able to pull this out. So this is what we call a duotransit, where we have 2 transits, but there's a large gap separating them. And in this case, we have some idea of the period. It can't be longer than 710 days or whatever the gap is, but we don't know which of the aliases this is. So there are actually hundreds of these cases where TESS has found them. Only about 1 in 4 have been found by the typical TESS detection pipelines and the TOI pipeline. So most of these aren't really publicly known. And there's a concentration, as you expect from the concentration of exoplanets around this sub-Neptune super-Earth regime. So the larger planets we can follow up from the ground, but we really need space-based observations to confirm and find the true orbits of these planets around, or these smaller planets. And that's where CHEOPS comes in. So as I said, we have many possible aliases, sometimes up to 40. But we have a minimum period determined by the light curve that we see, and the maximum period is the distance between the two transits. And then each of the subsequent aliases is some integer fraction of that maximum period. And we can actually use the data we have available from TESS to try and calculate which are the most likely periods. So that's something that I have some code which lots of people use to do this, which uses a transit model, also a prior on the period, prior on the eccentricity, because we know that planets on average have low eccentricities. So we can use that to derive something about the duration of the transit for each of the possible aliases. And in the case of multi-planet systems, we can also apply a stability prior. We can say that this outer planet cannot cross the orbit of an inner planet. So for eccentric orbits, that might be necessary in order to fit the data we have. So we can rule those out. And in this case, we actually have, this is a real case where we're able to narrow it down to basically 4 or 5 periods rather than the 12 that were possible initially. So this is a really useful step in order to reduce the amount of data that we need from CHEOPS. So this is an example with HIP 9618C, where there were 2 transits in TESS, and we went hunting with CHEOPS at different aliases. So 40 days, we saw a flat line, so ruled out that period. Did that again for 46 days, 48 days. We also failed again, but then at 52.6 days, we saw a beautiful transit. So we knew that the period of this sub-Neptune had to be at 52 days. So we've done that for a lot of planets now, nearing something like 20. And so these are the kind of results that we have that are published so far. So 7 systems published, where we have multiple planets. So I won't go through these in detail, but they mostly are orbit bright stars. So G is roughly a V magnitude. So below 10 is pretty bright. And they're mostly on orbits between 20 and 40 days. And so this is the kind of most recent publications where we have HIP 9618C, which I just showed you the light curves for, and then TOI 815, which Angelica Passaridi published earlier this year. And then there's this 6-planet system, which is a really interesting case, which Lupi published last year, and which I think this institute was actually involved in through Carmen. So I'll talk a little bit about that now, because that was a really interesting case. We started off with a test light curve that looked like this. So as before, you can see these clear dips in the light curve. So the only ones that seemed to match were these two, these pair of transits, which were about 9 days apart. So these ones looked like they were maybe one planet. And then all the other ones, we couldn't really work out what they were connected to, what the period would be. So we had to wait 2 years, and then TESS observed again. And this was the data from the first orbit, so just the first 10 days of 10 days of TESS observation. And once again, we see a bunch of transits here. So the 9-day planet was confirmed. So we saw 2 transits from the 9-day planet. So we knew that we had one of these planets where we knew the period. And then we saw another 4 transits where we were like, okay, we don't know what the true period is for these. Right? So of the 12 transits we had, only 4 of them made sense. So we waited and we got another orbit. So TESS gives orbits twice and gives you data at each orbit. So we were able to see another transit of B. And also we saw a periodicity for another set of transits, which we identified as planet C with her 13.7-day orbit. And then we found another transit we couldn't work out what it was connected to. So at this point, we had 6 transits, which we couldn't link to anything else. And so what I did was I modeled the transits individually to look at the duration and the depth effectively to try to tell, okay, can we link the transits we saw in the first year with the data we had 2 years later? And for two of these, we could actually do that quite well. So there are two kind of heat maps here which overlap. So this is planet D, and then this one here, which is the smallest of the targets. Once again, two transits overlapped very closely in parameter space. So we said, okay, let's match these together. And then there were two additional transits from the second year of observations where there was no good match for these. So these looked like we had two duo transits and two mono transits. And we roughly called them D, E, F, and G, but we actually had no idea of the order of these. It could be that this one was D and this one was F and this one was G, right? Because we didn't know the periods at this point for these four planets. So this is what the data looked like from TESS. We had beautiful transits for all of the planets, but we didn't actually know what the periods were except for the top two. So we went hunting with CHEOPS once again for the alias to try to confirm the periods. We also observed a couple of transits of planet B, and we were lucky enough to get a unique period for planet D, which confirmed it at 20.5 days. And this is when I looked at the data for this system, and I was like, this is interesting. Because if you look at the gap between these, this is almost 1.5, almost exactly. And actually the gap between these two, now we have 3 planets, is almost 1.5, like within 1 part per thousand. So this looks like maybe it's a resonance chain. And I confirmed with my colleague in Geneva, Adrien Deleu, and he confirmed that this was a Laplace resonance, the first 3 planets, just like TRAPPIST-1 or TOI-178. And so we had these 3 planets where we still didn't know the periods, but maybe we could use this information of it being a resonance chain to find those periods. So in the case of planet E, we had 24 aliases. It could have been any of them, most likely one of the shorter aliases, of course. But actually one of them was perfectly the exact same multiple of the period of C from D in the chain. So 1.5 once again. So this was too close to be coincidence. We said E must be on a 30.8 day orbit. Okay, so that left 2 more planets where we still didn't know the true periods, but we could do the same thing. We could look at all of the possible first order resonances for planet F, which would fit with the planet E that we assume, and try to figure out which of those is most likely. And actually, if you looked at the data we already had with TESS and CHEOPS, all but one of these, 6 to 5, 5 to 4, all but one of these periods would fall in a piece of data that we already had, and we had no transit there. So we knew that it couldn't be any of these aliases. The only one that was consistent was 4 to 3. So we said that this must be roughly 4 to 3 times the period of E, and we did the same for planet F. Once again, 2 of these were ruled out just by the photometry that we already had, and 2 more were ruled out because they weren't consistent with a Laplace resonance chain. So we once again said, okay, it's another 4 to 3 resonance with planet F. But at this point, these were just predictions. Even E, you could argue, was a prediction. We did try to get some ground-based photometry. So from across the kind of Western Hemisphere, Muscat 2, of course, at the IAC. And so we were able to potentially get a transit, but it wasn't high enough signal to noise to call planet F solved by this. Strong hints, though. And we also got radial velocities, so more than 250 RBs from both Carmenes and Harps North. So, of course, Carmenes is very closely connected with Grenada. And so this was, again, able to tell us something about the planets, and we were able to detect planet F at the period that we expected. So another sign that planet F was at 42 days. So this was the data that we had for photometrically going to publication, which was led by Rafa Luque in Nature last year. And then we got an email from someone in, I think, NASA Ames, who said, have you looked here? Because we assumed there was no data. It was masked out, or it was NAMs in the array. But actually, if you look at the raw data, there were 2 transits exactly where we predicted F and G to be. So we got really, really lucky here. And actually, the transit, I think, of planet F, this was 2 years away from the transit we had. And we predicted it within 5 minutes, which was incredibly impressive using this resonance chain. G was a little bit more out. I think it was about an hour off from where we predicted it, but incredibly precise prediction. So we were able to confirm the orbits of all 6 of these planets. And the really interesting thing about this system is that it's basically the brightest system with more than 3 transiting planets, the brightest resonance chain that we know about. It's like one of, if you look at the TSM, which is the expected signal to noise with JWST, all 6 are effectively among the most characterizable planets on long periods. And the reason this is interesting is we will be able to get really precise data from these planets just from the atmospheres. So we'll get C/O ratios from the atmospheric constituents, bulk water mass from the detection of water, both of those precise to about 10%. And that can tell us something about where is the rocky material in the system, because we only see gas-rich, volatile-rich planets. Where did they form? Are they water-rich, or are all sub-Neptunes water-rich potentially? And also just looking at the system longitudinally, we can ask, how compositionally varied are they, and how does the atmospheric composition change as a function of equilibrium temperature? Because we can basically probe 6 planets, perfectly primordial planets that haven't had any dynamical interaction as a function of temperature through the system. So this is something I've proposed like 4 or 5 times to JWST. So hopefully this last cycle 4, will be lucky, but we'll have to see. So going back to all of these geotransits that we've been observing, this is what they look like in terms of period. These are the ones that have been published. So we published a lot of multi-planet systems because those are more interesting, really. These are the ones that I'm currently working on publishing. Another 10 planets, including lots of single planet systems. And also I wanted to add this system, which isn't anywhere close to publication, but it looks almost identical to HD 110067. It's got resonances of precisely 1.5 throughout the system. And right now, CHEOPS is observing it. CHEOPS is trying to go for planet G. And if we see a transit in that data today, which we haven't got the data yet because CHEOPS is still looking at the star, then we'll be able to confirm that it's a resonance chain. It's also a young star as well, so only 300 mega years old. This planet is black because we haven't found it yet. We assume it's there because of the resonances, but we don't see it in the data yet. So that's a really interesting case that we are still working on. But yeah, I won't say the name, just kind of save that for next year, I guess. So yeah, in terms of all of these planets, they are, again, typically very bright, median of about 9. We have one around a naked eye star, which is only the 5th star found to host a planet. It's also the only one that has like a Neptune map or a Neptune-sized planet. It's Neptune radius, but actually the mass we have is below 5 Earth masses, so it seems to be very low density. It's a really interesting case, which I don't really have time to go into. If you look at the population in terms of the equilibrium temperature, they're also relatively cool, so between 400 and 600 Kelvin on average. So this is, for us, with transiting planets, we don't really go beyond Earth kind of orbits because you get to such long periods that it becomes impossible. So this is cool to transiting planet people, but obviously all of the solar system people are looking at this. 400 planets, that's hot, right? But 400 Kelvins is, for us, is relatively cool. And the interesting thing is that these are characterizable. So of the long period planets that we know about, the planets that we're finding with this CHEOPS program have some among the highest expected signal to noise planets beyond 20 days. So basically doubled the number of characterizable planets beyond 20 days. So in conclusion, well, I'm a little bit early, but that doesn't matter. So CHEOPS is a great instrument for characterizing and detecting sub-Neptune and super-Earth exoplanets. We've been able to do that via serendipitous observations, by using help from radial velocities, and also by using low signal to noise test candidates that weren't confirmed, in order to get, I think, 15 or so planets that way. And then this geotransit alley is also another really interesting way and prolific way of recovering long period planets, which we've done for about 20 cases now. In total, that makes about 40 new planets that CHEOPS has kind of contributed to. All of them are basically smaller than Neptune orbiting bright stars, and some of them will be characterized in the near future. And some of the key systems of this naked eye host of a transiting planet, obviously the 6-planet resonance chain, which Rafaluke published last year, and companions in 8 multi-systems as well. Yeah, lots more to come from CHEOPS there. So if you have any questions, please feel free to let me know, and hopefully I can chat with some of you later today. But yeah, I guess I should thank you all for coming. Thank you.
Thank you. Any questions?
Thank you for a very interesting talk. I have a question. Okay, I work here to do astroseismology, so I look at stars, and planets are basically the excuse we use to get funding. I wonder if you looked at the star properties for your systems, and if you, I don't know, if you found anything about metallicity, or, I mean, I guess you use the mass and the radius, but anything beyond that?
Yeah, I mean, unfortunately, we don't get astroseismology for these. TESS isn't quite as precise to be able to give us that. So we use Gaia astrometry and all of these survey photometric points to tell us the luminosities of these stars, and then we can compute precise radii. We get spectra, high-resolution spectra from Carmen's or HARPS or something like that in order to compute metallicities and things like that. And there are a few interesting cases where we have planets orbiting low metal poor stars, which are maybe from the thick disk or something like that. But it seems like in general the planets that we've been finding follow what the typical statistics you would see in terms of the local stars in the stellar neighborhood. So there's nothing in that respect interesting about the sample, I think. Yes.
Okay. Thank you for the talk. It was very helpful. I have 2 questions, if that's okay with you.
Sure.
One is, what is the expected lifetime of the CHEOPS mission?
I mean, right now CHEOPS is we have a lot of fuel, so fuel isn't an issue. The issue is that it's in a low Earth orbit, and the detectors are from like the 90s, because that's how slow ESA or the European space community is at getting things onto spacecraft. So the detectors have a really high hot pixel count. Every orbit or every day, the spacecraft passes through the South Atlantic anomaly, cosmic rays hit the detector. So currently, the detectors are about 10% hot pixel. So at the end of the extended mission, I think, or the second extended mission, which will be 2029, I think it will be about 20% hot pixel. And at some point, you don't have enough good pixels to do photometry with, and the hot pixels can vary and ruin things. So that's the main limiting factor, is actually the detector that's on board. So I don't think it will go beyond 2029. I think that'll be the solid end of life kind of time. Yeah.
That's sad.
Yeah.
Thank you. My other question was, you mentioned you have an amateur looking through your light curves. Is this similar to the Planet Hunters website, or?
Yeah. I think he started on Planet Hunters and then he went rogue. And yeah, he I don't know, just really likes finding planets, and but he's not a professional, so he doesn't know what to do with them when he finds them. So at some point, I got in contact with him through another project, and yeah, he just started sending me lists, and so he gets on the papers when we confirm these planets. But yeah, it's just an amateur who looks through a lot of light curves, I think, and a bunch of these systems we presented were initially at least started with his eyeballing, as we call it. Yeah, but Planet Hunters also finds sometimes overlapping array of these kind of single transits, and we do interact with them a little bit as well. So we pick up some of their candidates as well to confirm them. I think actually they independently found the HD11, the 6-planet resonant system. They were independently found that one as well. But not the periods, of course. So we have to do a bit more digging to be able to confirm those systems. Yeah.
Thank you for the talk. I am also from the Astroseismology group. I want to ask about how long the light curves of the unaccepted proposal are.
From which instrument?
From any of CHEOPS.
So CHEOPS, we typically only observe a transit. So we observe with CHEOPS for 12 to 16 hours in order to get the transit. So it's not long enough to get any astroseismic information.
Yeah.
Even though, well, I know for new to Lupi, they used it to get the stellar jitter, I think, or the some sort of information from the star, because it was a really long observation. But typically they're very short, half a day.
I was asking because we made with Andrea Bonfanti also a study to make to be sure if astroseismology could be useful, and if with 2 days or 1 day or less we cannot have a precise astroseismology, but a kind of some results can be useful to know the age or the radius and mass of the star.
Interesting. And that's more useful than 27 days of TESS, just because of the precision, or?
Yeah. Well, no, the TESS with 27 days is not useful.
Okay.
But just for stars that maybe TESS is not studying.
Yeah. Okay. Well, thanks.
So I was wondering how long they are to last for some time.
Yeah. So never more than 1 day, really.
Okay.
Yeah.
Okay. Thank you.
Hi, thanks for your nice talk. I'm studying planetary atmospheres. I'm not an observer. Probably it's something that I'm missing, and that's more a curiosity. If you go to one of the last slides, the conclusion, the conclusion, the last one, you say naked-eye transit hosts. What do you mean? Because my understanding, I have a bright star and you want to find a small planet, and also most of the planets, they have a long period orbit. What do you mean by naked eye transit? Because you would need a lot of observations in order to detect this small planet around the bright star. So something that I'm missing, I don't get this.
I mean, so naked eye transit host, I just mean that the magnitude of the host is less than 6 in this case.
Okay.
So the star is, if you look in the night sky in the south, you can actually see that the host star with the naked eye. The transit itself isn't naked eye observable.
What do you mean by ground-based observations?
Well, I just mean, so just that the host star is really bright. So a naked eye star is a star that's bright enough.
I see. Okay,
Yeah, sorry.
There was something I'm missing because I always I thought that's like you need a bright star, so the most favored transit are bigger planets. So I was didn't understand how you could detect a very small planets. Because you mentioned like amateur observation that help you also detect planets. So I thought you were mentioning something like this. Okay, now.
No, in our case, the amateurs, yeah. So you can do useful work with the giant planets with just small telescopes from the ground. But for these planets that we're observing with CHEOPS, they're too small to be observed from the ground as well. So the only work that amateurs do is look at the light curves and send us.
Because you need very, very high precision.
Yes. Yeah. Yeah. Even in the case of the campaign where we had 9 different professional observatories from the ground to try to confirm the period of this long period planet, we still couldn't say whether we found a transit or not. I mean, in hindsight, we know that we did. Because we know that the period was correct, but actually, when you do the Bayesian model comparison with this versus a straight line, it tells you that it could be either. So yeah, even with all of these observatories, from the ground we don't have the precision basically.
Any other questions? I have a very quick question actually.
Yeah.
Why was the data in that one masked or NANS, but it actually was there in the end anyway?
Yeah, I mean TESS is in this weird orbit where it's halfway to the moon at apoapse and very close to the Earth at perihelion. Periapse. Perigee, that's the one. And so often the Earth and the moon go into or close to the field. And so you end up with a large amount of scattered light, especially at the end or start of an orbit, which is when it's closest to the Earth, basically. And so what normally happens is that the scattered light is way too high and you don't see, the stars are dominated by scattered light, and so the data is not very useful. In this case, actually, if you look at the raw flux without doing any special detrending, it looks like a mess because the moon is in the field or something like that. So this group in NASA Ames had to do some serious kind of detrending to pull out the signals, but they're definitely there. But that was why it was masked in the first place. Yeah.
Okay. Yeah. Any other final question? No. Okay. So yeah, I guess we'll go and there. We will be going to lunch in 5 or 10 minutes, I think. So if anyone is free and want to join us, we'll be meeting just out at the front gates, or the front entrance rather. And otherwise, yeah, thanks for attending, and let's thank our speaker again.
Yeah.
Sure.